Time, for as long as we have understood it, has been a force that dictates every aspect of our existence. It governs everything from the ticking of the clock to the aging of our bodies, from the rise and fall of civilizations to the movement of the stars across the sky. Yet, despite its constant presence, time remains one of the greatest mysteries of the universe. Is it real? Or is it, as some thinkers suggest, merely an illusion, a construct of the human mind to make sense of the ever-changing world around us? Time seems like an undeniable truth. We feel its passage with every breath, see it in the cycles of the seasons, measure it with our clocks, and divide our lives into past, present, and future. But physics tells us something profoundly different. Time may not be as fixed and absolute as we think. Could time be a trick of the mind, a perception of reality that doesn't truly exist in the way we experience it? Can time be bent, warped, or even stopped? For centuries, philosophers and scientists have pondered the nature of time, and only in recent years has our understanding of it truly begun to unravel. Theories like Einstein's relativity and quantum mechanics have shown that time is not a simple, linear progression, but something far more elusive. It can be stretched, compressed, and even warped. It's not a constant, but something shaped by gravity, speed, and even the way we observe the world. In this journey, we'll explore the deepest questions of time: what it is, how we perceive it, and whether it is truly the unstoppable force we've always believed it to be, or merely a fleeting illusion in the grand narrative of existence. The nature of time. What is time? Time. What is it, really? We experience it constantly. Every moment, every heartbeat, every second that ticks away seems to affirm its existence. Yet, when we pause to ask what time truly is, the answer is elusive. Time is a concept, a measure, an experience. But is it a fundamental aspect of reality, or merely a human construct woven into the fabric of our consciousness? For most of human history, time was understood through a simplistic lens, something linear, like a river flowing from the past to the future. In ancient cultures, time was often seen in cycles, the day turning into night, the seasons repeating, life and death following an eternal rhythm. These cycles seemed to define time, giving it a sense of permanence and order. But with the dawn of modern science, our understanding of time began to shift dramatically. The first major transformation in our understanding of time came with Isaac Newton in the 17th century. Newton introduced the idea of absolute time, time that flows uniformly across the universe, independent of external factors. For Newton, time was a constant, ticking away at the same rate, whether you were on Earth or in the farthest reaches of space. It was the backdrop to the universe, a measure against which events could be ordered and understood. In Newton's view, time was an immutable force, as fundamental to the universe as space itself. It was a dimension that moved forward, from past to present to future, regardless of any object's movement or state. The universe, in this sense, was a grand clockwork mechanism, and time was its essential driver. But this view of time, though revolutionary, began to crack under the weight of new discoveries. In the 20th century, Albert Einstein's theory of relativity fundamentally changed our perception of time. According to relativity, time was not absolute. It could be bent, stretched, and altered depending on the speed of an object or its proximity to a massive gravitational source. Einstein's famous equation, E equals mc squared, showed that mass and energy were interchangeable, and that the fabric of spacetime could warp and curve. influencing the flow of time itself. Einstein's theory of relativity introduced a radical idea. Time and space were not separate entities, but part of a unified space-time continuum. Space and time were woven together, stretching and bending in response to the presence of mass and energy. Time, in this sense, was not a constant. It was relative. An observer on Earth would experience time differently from someone near a massive star, or traveling at speeds approaching the speed of light. Gravitational time dilation, the phenomenon where time moves slower in stronger gravitational fields, was confirmed with experiments. Clocks near the surface of the Earth ticked more slowly than clocks placed higher in altitude. This insight shattered the Newtonian view of time as a steady, uniform progression. Time was no longer an eternal, unchanging backdrop. It was a malleable, dynamic feature of the universe, influenced by the forces that governed the cosmos. The very fabric of reality was now seen as intertwined with time itself. Space and time were one. And yet, even as we have come to understand time as flexible, as warped by the forces of gravity and energy, we still find ourselves caught in the illusion of its unchanging flow. As we venture deeper into the mysteries of time, we must confront the question of whether time is truly as we experience it. Can we rely on our sense of time, or is there more to the story? Does time really pass in a linear fashion, or is it an illusion of perception, shaped by our minds and our limited perspective? In the chapters to come, we will dive deeper into these questions, exploring the nature of time from the perspective of both relativity and quantum mechanics, unraveling the ways in which time may be an illusion, shaped by the forces that govern the universe. The illusion of the present. Is the present real? If time is malleable, flexible, and relative, as Einstein's theory of relativity suggests, then we must ask ourselves, what does it mean to experience time as we do? When we look at the world around us, it appears as though time is flowing in a continuous stream, past, present, and future. But are we truly experiencing the present as it exists, or are we merely perceiving it through a filter of memory and expectation? The idea that the present moment is the only real moment, the now, has been central to human experience for millennia. We think of the present as the most immediate, the most tangible part of time, with the past fading away and the future still to come. But as we delve deeper into the nature of time, we begin to encounter a strange paradox. The present, as we experience it, may not be as real or as fixed as we think. To begin to unravel this mystery, we must first consider how we experience the present. Our perception of time is shaped by the brain's ability to process sensory information. What we experience as the present moment is actually a construction of our mind, a moment that is built from the past. The brain is constantly processing information and updating our awareness of the world around us. What we experience as now is actually a delayed reaction, as our brain takes a fraction of a second to interpret incoming stimuli. This delay means that our perception of the present is already a step removed from the actual moment we are experiencing. In other words, the present is not as instantaneous as we think. Instead, it is a moment that is always in the process of being constructed from past experiences. The more we try to grasp the present, the more it slips through our fingers as it's already gone by the time we become aware of it. This brings us to a striking realization. The present may be an illusion. This idea is not new. Philosophers have debated the nature of the present moment for centuries. Some have suggested that time is nothing more than a mental construct, a way for humans to make sense of the world. Others, like Immanuel Kant, argued that time and space are fundamental features of the human mind, a way of structuring experience, not inherent qualities of the external world. But the idea that the present moment is an illusion doesn't just arise from philosophy. It is also a question that physics forces us to confront. The theory of relativity, as proposed by Einstein, tells us that time is not the same for all observers. Time is relative. Its passage depends on the observer's speed and proximity to gravitational sources. If time can stretch and contract depending on one's position in space, then how can we be certain that any given moment is the same for everyone? The present we experience might not even be the same as the present that others experience in different parts of the universe. For instance, imagine two observers, one standing on the surface of the Earth and another traveling at near the speed of light in a spacecraft. The passage of time for the two observers would be vastly different. To the astronaut, the present would seem to move slower, while to the person on Earth, the astronaut's clock would seem to run faster. In this scenario, both observers are experiencing the present, but in very different ways. This leads to a deeper question. Is the present truly the same for everyone, or is it just an illusion created by our unique perspectives? Einstein's theory suggests that time is a deeply subjective experience, shaped by the observer's motion and the strength of gravitational forces. In a sense, time itself may be a reflection of how we perceive the world around us, not an absolute, unchanging reality. And if the present is relative, then what does that say about our experience of the now? One fascinating way to explore this idea is through the concept of the block universe, a theory that suggests that past, present, and future are all equally real. The block universe proposes that the entire timeline of the universe exists simultaneously, like a loaf of bread, with each slice representing a different moment in time. In this view, time is not a flowing river, but a static, unchanging structure. The past, present, and future all exist at once, and the passage of time is an illusion created by our consciousness moving along the timeline. In the block universe, the present is not privileged above the past and future. All moments are part of the same eternal block. This idea challenges the notion that the present is the only real moment in time, and instead suggests that all moments are equally real, each one existing as part of the larger fabric of the universe. If time is a block, then the distinction between past, present, and future is simply a matter of perspective, an artifact of human consciousness moving through the timeline. Yet, if the block universe is true, this leads to difficult questions about free will. If all moments in time exist simultaneously, then do we have any control over our actions? Are we simply following a predetermined path, unable to alter the course of events? This philosophical dilemma, known as the determinism versus free will debate, arises from the block universe concept. If time is already laid out, with all events set in stone, then how do we reconcile our sense of choice and agency? Despite the intriguing implications of the block universe theory, it remains a matter of speculation. There is no experimental evidence to support the idea that time is a static block. But the concept challenges us to rethink our deepest assumptions about the nature of time and reality. It forces us to question whether the present, as we experience it, is really the most important moment, or if it is just a fleeting perception, a tiny slice of an eternal, unchanging timeline. Moreover, the idea of time as a relative, subjective experience leads to another profound question. How does time relate to consciousness? Our experience of time is deeply tied to our awareness and perception of the world. We experience time as something that flows, something that passes from moment to moment. But if time is subjective, shaped by our individual perspectives, then our experience of the present moment might be more closely tied to our consciousness than to an external, objective reality. Is the flow of time something that emerges from the brain, shaped by the way we process information, or is it a fundamental feature of the universe that we merely perceive? These questions reveal the mystery of time, a mystery that goes beyond the laws of physics and into the realm of consciousness and perception. The nature of the present moment, and whether it is real, may ultimately be something we can never fully understand. As we continue to explore the mysteries of time, we are forced to confront the possibility that our experience of time is just an illusion, a trick of the mind, shaped by the way we perceive the world and our place within it. Quantum mechanics and time, the uncertainty of reality. As we explore the nature of time, our journey leads us deeper into the most perplexing and enigmatic realm of modern physics, the quantum world. Here, the laws of classical physics break down, and time itself behaves in ways that defy our everyday experience. In the quantum realm, particles exist in a state of constant uncertainty, shifting between possibilities and probabilities, rather than following fixed paths. Time, in this strange and mysterious domain, becomes even more elusive. At the heart of quantum mechanics lies the idea of quantum superposition, the notion that particles can exist in multiple states at once, occupying different locations or configurations simultaneously. Unlike classical objects, which have definite positions and velocities, quantum particles are described by a wave function, which encompasses all the possible states they could occupy. It is only when we measure the particle that its wave function collapses, and the particle chooses a definite state. Until that moment, the particle exists in a superposition of all possible states, meaning that the concept of time, in the traditional sense, is meaningless. Time itself seems to be suspended, or at least obscured by this uncertainty. For instance, imagine an electron that can be in two places at once. It is not moving from one place to another as we would expect in the macroscopic world. Instead, it exists in a probabilistic cloud of potential locations until we observe it. This challenges our perception of time as a linear, ordered progression. If the behavior of particles at the quantum level is not determined until we measure them, does time exist for these particles in the same way it does for larger objects? Heisenberg's uncertainty principle, another fundamental feature of quantum mechanics, further complicates our understanding of time. According to this principle, we can never know both the position and momentum of a particle with complete certainty. The more precisely we measure one, the less precisely we can know the other. This inherent uncertainty extends to our understanding of time itself. If the position of a particle is not well defined, how can we speak of the passage of time in a way that aligns with our usual understanding of the flow of events? Is time in the quantum realm itself subject to uncertainty? These principles, superposition and uncertainty, suggest that time may not be a continuous flowing phenomenon at the quantum level. Instead, it may be disjointed and fragmented, an aspect of reality that we cannot fully grasp using the tools and frameworks we are familiar with. Time, at this scale, is not a steady river of moments, but a hazy collection of possibilities that only solidifies into a concrete reality once we observe it. This quantum view of time challenges the very nature of reality. If time is not an unbroken stream, but a construct shaped by the act of observation, what does this imply for the nature of causality, the relationship between cause and effect? In classical physics, the cause always precedes the effect, creating a clear, linear progression. But in the quantum realm, the sequence of events becomes blurred. Quantum entanglement, in which particles instantaneously affect each other over vast distances, defies the idea of a linear cause and effect. Can time even flow in a straightforward manner if particles can influence one another faster than the speed of light, without a direct, observable cause? Perhaps even more troubling is the idea of time travel in the quantum world. In classical mechanics, time is irreversible. We cannot move backward in time. The arrow of time moves forward, from past to future. But quantum mechanics seems to suggest that time is far more fluid and malleable. The possibility of quantum tunneling, where particles can pass through barriers that they shouldn't be able to cross, hints at the idea that time, too, might not be as rigid as we think. Could the particles move backward in time, just as they move backward through space? If so, what does this imply about the flow of time in the universe at large? Furthermore, quantum mechanics suggests that time, much like space, might be quantized, that is, made up of discrete units. If time is quantized, it would be composed of tiny time atoms, similar to how matter is made up of atoms. This idea is still speculative, but if true, it could radically change our understanding of time. Rather than being a continuous flow, time might consist of small, indivisible units that cannot be divided any further. This would align with loop quantum gravity, a theory that suggests space-time itself is quantized, made up of discrete loops of gravitational fields. If time is quantized, could it be that the flow of time itself is not a smooth continuum, but a series of staccato moments, tiny intervals that our minds smooth over to create the illusion of continuity? These quantum ideas, though mind-bending, suggest that time at the fundamental level is vastly different from the time we experience in our daily lives. While we perceive time as a flowing river, constant and unchanging, the quantum world reveals a very different picture. Time is not a fixed, continuous quantity. Instead, it is a malleable, uncertain force, one that is shaped by the principles of probability, superposition, and the act of observation itself. Time is not a rigid backdrop to events, but a dynamic participant in the unfolding of the universe, constantly shifting and changing as the quantum world dictates. But if time behaves so unpredictably at the quantum level, what does that mean for our understanding of the macroscopic world, the world we interact with on a daily basis? How can the smooth, continuous passage of time that we experience in our everyday lives emerge from such an uncertain, fragmented quantum foundation? This question leads us into the heart of one of the greatest mysteries of modern physics, the search for a unified theory of quantum gravity, which would reconcile the strange world of quantum mechanics with the smooth, predictable behavior of general relativity. Until we understand how time works on both the quantum and cosmological scales, the true nature of time will remain elusive. In the next chapter, we will explore the paradoxes of time travel and how quantum mechanics might provide a framework for understanding the seemingly impossible. Moving backward through time, altering the course of events, and challenging the very fabric of cause and effect. Time, as we will discover, may not be the unchangeable constant we once thought. It is a dynamic, uncertain, and deeply mysterious force, one that could hold the key to understanding the ultimate nature of the universe. Time in the theory of relativity. Is time relative? We've already seen that time is far more elusive than we might have imagined. But the most profound shift in our understanding of time came in the early 20th century with Albert Einstein's theory of relativity. Einstein's insights did not just change our understanding of time, they fundamentally redefined it. Time, as we had always perceived it, as a constant ticking clock that passed uniformly for everyone, was a deceptive illusion. Einstein's revelations made it clear that time is not absolute. It is relative. Special relativity, introduced by Einstein in 1905, was the first of his theories to shake the foundation of classical physics. It was based on a simple but profound insight. The laws of physics are the same for all observers, no matter how fast they are moving. For example, the speed of light in a vacuum is constant. No matter how fast you are moving or in what direction, light always travels at the same speed. This was a departure from the classical view, where velocities were simply added or subtracted based on the relative motion of the observer. The relativity of time is perhaps the most startling consequence of Einstein's theory. According to special relativity, time does not flow at the same rate for everyone. The faster an object moves, the slower time passes for it, relative to an observer at rest. This phenomenon is known as time dilation. It might sound counterintuitive, but it has been experimentally verified in many ways, most famously through experiments involving atomic clocks. Imagine a spaceship traveling at a speed close to the speed of light. If the astronaut on board were to set off on a journey into deep space and then return to Earth, they would find that far more time had passed for the people on Earth than for them. The astronaut's clock would have ticked more slowly than the clocks of those left behind. This difference in the passage of time is not just theoretical, it has been observed in real-world experiments. Atomic clocks flown on airplanes, for example, ticked slightly slower than identical clocks left on the ground, a phenomenon that can only be explained by relativity. This effect, time dilation, becomes particularly dramatic as objects approach the speed of light. As an object moves faster and faster, the passage of time for it slows down more and more relative to stationary observers. If we could somehow travel at light speed, time would essentially stand still for the traveler. But since the speed of light is the ultimate speed limit of the universe, this scenario remains theoretical for objects with mass, as they would require infinite energy to reach the speed of light. At the heart of Einstein's insight is the idea that time is not a universal, objective entity, but something relative. It is shaped by motion, by velocity, and by the strength of gravitational fields. The fabric of space-time is a dynamic structure, influenced by the motion of objects and the presence of mass and energy. The stretching of space-time caused by massive objects creates gravitational time dilation, where time runs slower near a massive object, like a planet or a black hole, than it does far away from such objects. This concept of time as a flexible, malleable entity is reinforced by general relativity, Einstein's later theory of gravity introduced in 1915. While special relativity dealt with the behavior of objects moving at constant speeds, general relativity expanded the theory to include objects that were accelerating or experiencing gravitational forces. The key insight of general relativity is that gravity is not a force that acts between objects, as Newton had proposed. Instead, gravity is a result of the curvature of space-time itself. Imagine placing a heavy ball on a rubber sheet. The ball causes the sheet to bend, creating a depression. Now, if you roll a smaller ball across the sheet, it will move toward the heavy ball, not because of a direct force, but because the sheet itself is curved. In the same way, massive objects like stars and planets bend space-time, and this curvature affects the motion of other objects within it. Time, too, is affected by this curvature. Near a massive object, like a black hole, time slows down, relative to an observer far away from the object. This gravitational time dilation has been observed in experiments where clocks placed at different altitudes, even within the Earth's gravitational field, tick at different rates. The stronger the gravitational pull, the slower time moves. Near the event horizon of a black hole, time essentially stops from the perspective of an outside observer. To someone falling into a black hole, time would seem to pass normally for them, but for someone watching from a safe distance, their clock would appear to slow to a crawl as they approached the event horizon. Time's relativity, both through motion and gravity, reveals a profound truth about the nature of the universe. Time, like space, is not a fixed, absolute concept. It is a fluid, dynamic force, shaped by the very structure of space-time. In fact, time and space are so intertwined that we cannot separate them. Space-time is a unified whole. The events we observe are not located in space and time independently. They are located in space-time. This insight fundamentally changes how we view the universe. We can no longer think of time as a separate dimension, moving independently of space. Time and space are intimately connected, and their interplay determines the nature of reality itself. But if time is so malleable, so relative, then what does it mean for our everyday experience? For centuries, we've assumed that time is a constant, that it moves forward in a linear fashion for all observers, regardless of where they are or how they're moving. The ticking of the clock seemed to be the one true, unwavering aspect of the universe. But Einstein's theory forces us to confront a reality where time is not so reliable, not so absolute. In this world, time may stretch and shrink, slow down and speed up, depending on the context. This leaves us with several perplexing questions. If time can be manipulated so easily, is our perception of time as it flows through our daily lives just an illusion? Are we perceiving a reality that is shaped by our own limitations as observers? And if time is relative, is there an objective time, an absolute clock that exists independent of us, or is time itself just a part of the illusion of reality, shaped by the forces around us? Time's elasticity is not just a curiosity or a theoretical notion. It holds the key to some of the most fundamental aspects of the universe. It shapes the movement of stars, the formation of galaxies, and even the way light travels across the vastness of space. But more than that, it forces us to rethink the very nature of reality itself. Time, it turns out, is not an unchanging river that flows relentlessly forward. It is a malleable, relative experience, shaped by motion, by gravity, by the very structure of space-time. In the next chapter, we will delve deeper into the phenomenon of gravitational time dilation, exploring how massive objects and intense gravitational fields warp our perception of time. We will also examine the implications of these insights on our understanding of the universe's evolution, from the formation of black holes to the mysteries of dark energy and the eventual fate of the cosmos. The arrow of time. Why does time only move forward? Time, for all its flexibility and malleability, seems to possess an inescapable quality. It flows forward. While the universe's most fundamental laws of physics, such as Newton's laws of motion, electromagnetism, and quantum mechanics, do not prefer a specific direction of time. Our experience of time is inexorably tied to a one-way, forward-moving flow. We age, events unfold, and the past fades into history. But why is it that time only moves in one direction? Why does the past remain fixed and the future remain elusive? This concept, known as the arrow of time, is one of the most perplexing and enduring puzzles in physics and philosophy. While the fundamental laws of physics can, in theory, operate equally well forwards and backwards in time, our experience of time is marked by a clear direction. The present flows into the future, and the past is behind us. Everything from the unfolding of life to the aging of stars seems governed by this one-way progression of time. But what dictates this forward flow? The answer to this question lies in the concept of entropy. In thermodynamics, entropy is a measure of the disorder or randomness in a system. According to the second law of thermodynamics, the entropy of a closed system tends to increase over time. In simple terms, systems move from a state of lower entropy, more order, to a state of higher entropy, more disorder. This natural tendency toward increased disorder gives rise to the forward flow of time. Think of a cup of coffee. If you place a spoonful of sugar into it, the sugar will dissolve, and over time, the sugar molecules will spread out evenly throughout the liquid. The system moves from a low entropy state, where the sugar is concentrated, to a higher entropy state, where the sugar is evenly distributed. The process is irreversible. Once the sugar has dissolved, it won't spontaneously clump together again. The increasing disorder, or entropy, marks the passage of time. As entropy increases, the system moves forward, and the past remains in a lower entropy, more ordered state. This tendency for systems to increase in entropy is not just a rule of thermodynamics, it is what gives time its directionality. The arrow of time, in this sense, is a reflection of the universe's tendency to evolve from states of lower entropy to states of higher entropy. The flow of time from past to future is tied directly to the increase in disorder in the universe. In fact, many physicists believe that the very nature of time is tied to the second law of thermodynamics. The irreversible increase in entropy provides the arrow that gives the time its one-way flow. The universe, from the moment of the Big Bang, has been steadily moving toward a state of greater disorder. Stars burn out, galaxies drift apart, and even black holes slowly lose energy over time. The overall trend is toward greater entropy and a universe that becomes more and more disordered, less structured, and ultimately more uniform. But while the idea of entropy provides a compelling explanation for why time seems to move forward, it also raises deeper questions about the ultimate fate of the universe. As entropy increases, the universe moves closer to a state known as thermodynamic equilibrium, a condition in which all matter and energy are evenly distributed, and no further work can be done. This state, often referred to as the heat death of the universe, represents the end of time's forward progression. In a universe at maximum entropy, there would be no gradients of energy, no differences between hot and cold, no stars or galaxies to fuel the processes of life or cosmic evolution. Time, in this sense, would come to a halt, as there would be no events to mark its passage. In this state of maximum entropy, the arrow of time would have nowhere to go. The universe would become a cold, dark, lifeless expanse where nothing changes, and the passage of time would cease to have any meaning. Everything would be uniform and stagnant, without energy to fuel the processes of change. The forward flow of time, governed by the increase in entropy, would find no further purpose or direction. However, despite the inevitability of this heat-death scenario, there is still much we do not understand about entropy and the nature of time. For instance, while entropy tends to increase over time in isolated systems, what about the universe as a whole? Some theories suggest that the universe itself could experience a form of cosmic recycling, where the universe undergoes repeated cycles of expansion and contraction, resetting the entropy between each cycle. This Big Bang Big Crunch cycle could potentially allow the universe to avoid an eventual heat death, perpetuating the forward flow of time indefinitely. In such a scenario, the universe would experience a new beginning each time, where the entropy starts fresh with each new cycle. But even this cyclical view does not entirely solve the mystery of time's directionality. Why is entropy the defining characteristic of the arrow of time? Why do some processes, like the dissolving of sugar in coffee or the cooling of a hot object, move in one direction and not the other? The universe could, in theory, have started in a high entropy state, where everything was already disordered and random, but instead, we find that it began in a very low entropy state, highly ordered and structured. This presents a conundrum. Why did the universe start in such a low entropy state? What caused this initial condition? And why does the universe follow the second law of thermodynamics from that point onward? Some physicists have speculated that the initial low entropy state of the universe could be linked to the nature of the Big Bang itself. In the moments following the Big Bang, the universe was incredibly hot and dense, and as it rapidly expanded, it moved toward a state of greater entropy. The second law of thermodynamics, which governs the increase of entropy, was already set in motion by the universe's expansion. But the question remains, could there be other processes beyond entropy that govern the flow of time? Quantum mechanics, for example, suggests that time may not be as straightforward as we think. In the quantum world, particles can move backward in time, or appear to do so in certain conditions. Quantum entanglement, where particles remain connected over vast distances, seems to violate the traditional understanding of cause and effect. Could time's flow not be the simple unidirectional progression we experience? Could it be more fluid, influenced by quantum fluctuations, and not bound by the second law of thermodynamics? In this chapter, we've explored how the flow of time is linked to the universe's increasing entropy. The forward movement of time, the arrow of time, appears to be tied directly to the universe's inevitable increase in disorder. However, the deeper we look into the nature of time, the more we realize that its forward flow is not as simple and inevitable as we once thought. The increase of entropy is only one part of the story. The true nature of time, its origins, its direction, and its eventual fate, remains one of the greatest mysteries in physics and philosophy. And in the coming chapters, we will explore these questions further, delving into the complexities of time in both the quantum and cosmological realms. The Block Universe. Time as a dimension. As we continue our exploration into the nature of time, we are faced with one of the most fascinating and challenging concepts in modern physics, the Block Universe. This theory, also known as eternalism, proposes a radically different view of time. Instead of time being a flowing river with past, present, and future in constant motion, the Block Universe suggests that time exists as a static entity, where the past, present, and future all coexist simultaneously. In this view, time is not a flowing progression. It is a dimension, much like space, where all events, past, present, and future, are laid out in a fixed, unchanging structure. This theory is a direct challenge to our everyday experience of time. We experience time as a sequence, an unfolding story that moves from the past through the present and into the future. But in the block universe, there is no movement from one moment to the next. Instead, all moments in time exist equally, and the only thing that changes is our perspective as we move through them. The block universe is an extension of the space-time continuum described by Einstein's theory of relativity. In relativity, space and time are fused into a single, four-dimensional entity, space-time, that is shaped by gravity and the motion of objects. Events are not located at specific points in time and space, but at points in space-time, which combines both the dimensions of space and the dimension of time. Just as we can describe the position of an object in three-dimensional space, we can describe its position in space-time. But in the block universe, time is not something that flows or progresses. It is a part of this four-dimensional structure, where all events are set within the fabric of space-time. The block universe theory suggests that every moment in time, from the beginning of the universe to its eventual end, exists simultaneously. The past, present, and future are not separate entities, but are part of the same eternal block. The present moment that we experience is merely the point from which we observe this block, but it is not a special or unique point in time. All moments are equally real. This view stands in stark contrast to our everyday experience, in which we perceive the present as the only real moment, the past as gone, and the future as yet to come. In this context, the arrow of time, which we usually associate with the flow from past to future, is simply an illusion of perspective. It is a result of our conscious experience as we move through the block universe. Our minds are wired to perceive events as moving forward in time, but this perception does not reflect the underlying structure of the universe. The block universe suggests that the future already exists, just as the past does, and all of time is laid out before us. We, as conscious beings, are simply moving through the timeline, experiencing one moment after another in a way that feels like progression, but in reality, every moment is already fixed. This view raises profound philosophical questions about free will, choice, and determinism. If the future already exists within the block universe, then what room is there for free will? Do we have the ability to shape our future, or is everything predestined, laid out in the fabric of space-time? If time is a static block, then all events, including our actions, have already occurred, just as the past has already happened. Our sense of choice becomes an illusion, because everything we do is simply a part of the grand, unchanging structure of the universe. Many philosophers and physicists who support the block universe theory argue that our experience of free will is still valid, even if the future is already set. While our actions may be part of a fixed block, they are still our actions, and we experience them as choices. The block universe does not negate the experience of living. It simply redefines the way we understand time. In this view, time is not an unfolding narrative. It is a fixed structure that we move through, but it does not make our lives or our actions any less real or meaningful. We are not actors in a predetermined play. Rather, we are participants in a universe where all events, including our own lives, coexist in an eternal block. One of the most intriguing aspects of the block universe theory is its connection to the nature of light and the speed of light. In special relativity, the speed of light is considered to be a constant. Nothing can travel faster than light. This means that light, in a sense, defines time. The way we experience the passage of time is tied to the speed of light, as the speed at which light travels across space determines how we measure the distance between events in space-time. But in the block universe, this constancy of light leads to another paradox. If all events in the universe exist simultaneously, then how do we reconcile the fact that light takes time to travel across vast distances? When we observe distant stars or galaxies, we are seeing them as they were in the past, not as they are now. The light from those objects has traveled across space for millions or even billions of years. But in the block universe, the events that occurred in the past are just as real as the events unfolding in the present. The light we see from distant stars is not just a record of the past. It is a window into the eternal block of space-time, where all events exist at once. In this view, the past, present, and future are not separate, but part of a unified whole. The universe is not moving through time in a linear fashion. It is a timeless structure, where all moments are laid out before us, waiting to be observed. Our experience of time, then, is a result of our conscious perspective moving through the block, not a fundamental aspect of reality. Time, as we understand it, is an illusion, one shaped by our minds and our perception of the universe. The block universe theory has far-reaching implications not just for physics, but for our understanding of existence itself. If time is a fixed structure, then what does it mean for our consciousness? What does it mean for our sense of self? Are we just passengers moving through a predetermined universe, or are we more than that? Active participants in the cosmic dance, even if the steps have already been written. As we continue to explore the mysteries of time, we must confront these deeper questions. The block universe invites us to reconsider the nature of time and our place in it. It challenges us to rethink our experience of the present moment and what it means to live in a world where the future, past, and present all exist together in a grand, unchanging block. In the next chapter, we will explore the flow of time. Why do we experience time as a continuous river? And how does our mind create the illusion of its passage? We will also delve into how the block universe theory relates to other models of time and how it changes our understanding of free will, causality, and the nature of reality. The flow of time. Why do we experience time as a flow? As we continue to explore the mysteries of time, we are confronted with one of the most fundamental aspects of our experience. We perceive time as flowing, a river that moves forward from the past into the future. We feel time's passage in everything we do. Our hearts beat, our clocks tick, the world turns, and we measure the flow of time with every breath we take. Time feels real, tangible, as though it is something that we are carried along with, an invisible current sweeping us from one moment to the next. But if time is truly a dimension, a part of the space-time continuum, why does it feel so one-directional, so linear? Why do we perceive time as something that flows forward, always toward the future, never backward to the past? Why is the past fixed, the future uncertain, and the present fleeting? The sensation of time's flow, its arrow, is not just a trivial part of our experience. It shapes everything we know about the universe. From the aging of our bodies to the evolution of galaxies, everything in the cosmos seems to follow a distinct path, from past to future. But is this sensation of time's passage something fundamental about reality? Or is it simply a mental construct shaped by the way we perceive the world around us? One of the most compelling ways to understand why we experience time as flowing lies in the second law of thermodynamics, which we encountered earlier in our discussion of entropy. This law states that in any closed system, the total entropy or disorder of that system will always tend to increase over time. In simple terms, the universe moves from a state of greater order to greater disorder. But this progression of disorder is what gives the time its directionality. When you open a jar of perfume, for example, the molecules of the perfume spread out and diffuse through the air, moving from a state of high concentration to low concentration. This process of diffusion is irreversible. The perfume molecules will never spontaneously reconcentrate in the jar. The movement from ordered to disordered states, from lower entropy to higher entropy, gives time its forward momentum. This is what makes time feel like it flows. As we move through time, the universe becomes more disordered, and this natural progression marks the passage of time. But while the second law of thermodynamics explains the directionality of time, the arrow pointing from past to future, it doesn't explain why we perceive time as flowing. After all, the laws of physics themselves, whether in classical mechanics or quantum mechanics, are time-symmetric, meaning that they work equally well whether time is moving forwards or backwards. In the equations of physics, time could just as easily run backward as it does forward. Yet our experience of time is fundamentally asymmetrical. To understand why time feels like it flows, we must look at consciousness, how our minds process and perceive time. Human beings are uniquely equipped with the ability to experience the passage of time in a way that no other known entities can. We remember the past, we live in the present, and we anticipate the future. Our perception of time, in other words, is bound up with our experience of change, of events unfolding one after another in an irreversible sequence. The mind, like the universe, is constantly changing. Our thoughts evolve, our memories fade, and our bodies age. Every moment, every experience seems to be a snapshot in the flow of time, and it is this constant flow of change that shapes our perception of time. In some ways, we are like the rest of the universe, perpetually moving through states of increasing entropy. Our minds, too, are shaped by the forces of change, the flow of moments from past to present to future. But why is this experience of time, this mental flow, so linear? What is it that makes the past fixed, the future uncertain, and the present moment ever fleeting? One of the answers may lie in our memories. Our ability to remember the past and anticipate the future is central to our experience of time. Memories create a bridge between the past and the present, while our imagination creates the bridge between the present and the future. It is this memory and anticipation that may be responsible for the illusion of time's flow. The mind, in its constant quest to make sense of the world, constructs a narrative, an ongoing story of events. This narrative is inherently linear because we cannot remember the future, and we cannot experience the future until it becomes the present. This sense of continuous unfolding events, where one moment leads naturally to the next, is what gives time its apparent flow. However, this linear perception may also be a psychological limitation. The passage of time is shaped by the way we process information, by the way we encode and store memories. If we could somehow process time differently, if we could perceive the future as we perceive the past, would we experience time as more of a simultaneous whole? Or would our understanding of time and our place within it shift entirely. In many ways, the illusion of time's flow mirrors the way the mind organizes the world. We seek to impose order on a universe that is inherently unpredictable and uncertain. Our minds create the sensation of time's movement, just as they create the illusion of a stable, continuous present. If the past is a record of memories and the future is a canvas of possibility, the present is the narrow sliver where we live, and it is in this sliver that time's flow feels most real. But, as we've learned, time is not merely a mental construct. The physics of time tells us that time, as we perceive it, is deeply intertwined with the forces of the universe. Time is not just a psychological experience. It is an intrinsic part of the cosmos, shaped by the fabric of space-time, by the speed of light, and by the motion of mass and energy. While we experience time as linear and flowing, the true nature of time may be far more complex, far more interwoven with the fundamental forces of the universe than we could have ever imagined. This realization, that time's flow is deeply tied to our perception and our consciousness, opens up new possibilities for understanding time itself. Could there be a way to perceive time differently, to experience the past, present, and future as a unified whole? Could we transcend the illusion of time's forward movement, stepping outside the boundaries of our limited perspective? In the next chapter, we will explore how the concept of time travel challenges our understanding of time's flow. If time is so deeply tied to perception, to the fabric of space-time, can we ever step outside this flow? What does it mean for time to be bent, stretched, and traversed in ways we have yet to fully comprehend? Time travel, science fiction or scientific possibility? The concept of time travel has captivated human imagination for centuries. From the pages of H.G. Wells's The Time Machine to modern-day films like Interstellar and Back to the Future, the idea of traveling through time, whether to the past or the future, has fascinated us in ways both philosophical and practical. It poses a question that challenges everything we think we know about time. Is time something we can move through, like a river, or is it fixed, an immovable force that flows in one direction? The possibility of time travel touches on the most fundamental aspects of time itself. If time is a flowing, one-way river, can we swim against the current, or even move backward in time? What would it mean to travel to the past? Would you change the future? Or would the universe somehow protect itself from paradoxes? And how could time travel to the future be possible if time, as we experience it, seems so linear? In the realm of physics, the possibility of time travel is not as outlandish as it may first appear. In fact, Einstein's theory of relativity provides a theoretical framework for time travel, though it is far more complex than simply hopping into a time machine. Relativity has shown us that time is not a constant. It can stretch, contract, and even bend depending on the speed of an object and the strength of the gravitational fields it is in. This opens the door to the possibility of time dilation, the slowing or speeding up of time relative to an observer's motion or gravitational field. Time travel to the future. The speed of light and gravitational time dilation. Perhaps the simplest way to imagine time travel is in the context of traveling to the future. We know from Einstein's special relativity that time moves slower for objects moving at speeds close to the speed of light. This phenomenon, called time dilation, means that if you were to travel in a spaceship at a speed close to light, time on board the ship would pass much slower than time on Earth. A few years of travel on the ship could correspond to decades, or even centuries on Earth. In essence, you would be traveling to the future. This idea has been confirmed experimentally. For example, atomic clocks flown on airplanes or placed on satellites tick more slowly than identical clocks on Earth, due to both special relativistic time dilation, due to the speed of the aircraft, and gravitational time dilation, due to the difference in altitude. As we approach the speed of light, the time dilation effects become more pronounced. At 99% of the speed of light, for example, time on the ship would pass at a rate 7 times slower than on Earth. At 99.99% of the speed of light, time would slow down by a factor of 70. In theory, if we could build a spaceship capable of traveling at a substantial fraction of the speed of light, we could travel to the future of Earth. The faster we travel, the more time slows for us, allowing us to effectively leap forward in time. But this is not something we can easily achieve with current technology. To reach even a fraction of the speed of light requires an unimaginable amount of energy, far beyond our present capabilities. However, time travel to the future, at least in theory, is not a violation of physics. It is a direct consequence of our understanding of relativity. Time travel to the past. The paradoxes of history. If traveling to the future seems plausible, what about traveling to the past? Here, the question becomes far more complicated, not only from a scientific perspective, but from a philosophical one as well. Can we change the past? And if we can, what are the implications for the present and future? The primary issue with time travel to the past is the possibility of causal paradoxes. Situations where the act of traveling to the past creates contradictions that seem to defy the laws of logic. One of the most famous paradoxes is the grandfather paradox. If you travel back in time and accidentally prevent your grandfather from meeting your grandmother, you would prevent your own birth. But if you were never born, how could you have traveled back in time in the first place? The very act of changing the past would seem to negate your ability to change it. There are several theoretical solutions to this problem. One of the most well-known is the idea of closed time-like curves, CTCS, which arise from the equations of general relativity. CTCS are paths in spacetime that loop back on themselves, creating a closed loop. This means that time would eventually return to its starting point, allowing for travel to the past. Some physicists believe that if CTCs exist, they could allow time travel to the past without violating causality. The events that unfold in a closed loop would still follow a consistent, self-contained sequence, avoiding paradoxes by ensuring that the timeline is self-consistent. However, CTCs are still purely theoretical. While they arise from the equations of general relativity, there is no experimental evidence to suggest they exist in nature. And even if CTCs do exist, they may not allow for the kind of free travel we often envision. The idea that we could freely visit the past and change history may still be far beyond our reach, as the equations that allow for time loops may only work under very extreme conditions, such as near a rotating black hole. Another intriguing possibility comes from wormholes, hypothetical bridges in space-time that could connect distant regions of the universe or even different points in time. If a wormhole could be stabilized and manipulated, it might provide a pathway for time travel to the past. However, the existence of wormholes is speculative, and there is currently no way to create or stabilize them. Theoretical physicists have suggested that if wormholes do exist, they could provide a shortcut through space-time, potentially linking different eras of time. But, like CTCs, wormholes remain theoretical constructs that have yet to be proven or observed. Time travel and the limits of physics. Despite these possibilities, there are deeper issues with time travel that lie at the core of our understanding of the universe. In particular, general relativity and quantum mechanics seem to conflict on whether time travel is truly possible. General relativity allows for time travel through CTCS or wormholes, but quantum mechanics, especially when it comes to quantum entanglement, suggests that time may be governed by a different set of principles entirely. One of the key issues lies in the potential destruction of causality. The very concept of time travel challenges the idea that cause precedes effect. If we can travel to the past and change events, we violate the fundamental principle that the present moment is shaped by the events that came before it. This creates a situation that is unpredictable, potentially breaking the laws of physics and leading to chaos in the fabric of space-time. Furthermore, as we approach the Planck scale, the smallest scale of space and time, our current understanding of both general relativity and quantum mechanics breaks down entirely. At this scale, the fabric of space-time becomes quantized, and the rules governing time may be fundamentally different from those at larger scales. Some physicists argue that time itself may lose its meaning at the Planck scale, suggesting that time, as we experience it, may not even be a valid concept at the quantum level. In this way, time travel to the past, while tantalizing, remains far from possible. It is bound by both theoretical limitations in our understanding of space-time and the fundamental paradoxes it presents. However, the exploration of time travel remains a key area of research, as it forces us to confront the limits of physics, causality, and the nature of time itself. The future of time travel. Is it possible? As we continue to probe the mysteries of time travel, we come to an inescapable conclusion. Time travel, as we imagine it, is not yet a reality. The possibility of traveling to the future is grounded in the theory of relativity, and with advances in technology, we may one day be able to explore the future in ways previously thought impossible. But traveling to the past presents more profound challenges, ones that may be beyond the reach of current physics. Time travel forces us to confront our deepest assumptions about the nature of time, space, and reality. It invites us to reconsider the very flow of time, the forward progression that we experience every day. And in the process, it opens new doors to understanding the universe, revealing that time, like space, may not be as straightforward as we once believed. The nature of consciousness. How does time relate to our perception? As we have journeyed through the physics of time, from relativity to quantum mechanics, we are now compelled to confront one of the most profound and perplexing connections between time and the human experience: the relationship between time and consciousness. Our perception of time is perhaps the most personal and intimate of all our experiences. Time dictates the rhythm of our lives, the moments we remember, the events we anticipate, and the fleeting present that we live through. But if time is as fluid, malleable, and elusive as modern physics suggests, how is it that we experience it in such a fixed, unchanging way? The experience of time is central to our consciousness. As we move through the world, we are acutely aware of the passage of time. We wake up in the morning and mark the passage of time as we go about our daily tasks. Our memories carry us into the past. Our anticipations carry us into the future and the present moment. The only moment we can truly live in slips through our fingers as it constantly recedes. But while our subjective experience of time feels like a constant flow, our consciousness of time is, in fact, shaped by our brain's perception and our internal sense of how the world is changing around us. So, how do our brains create this experience of time? And why does it feel so linear, so unyielding? To answer this, we must first understand how our brain processes information and how it organizes the flow of events. The brain is not simply a passive observer of the world. It actively constructs our perception of reality, creating a narrative of cause and effect that spans across time. Time, in this sense, is not an independent force but is deeply intertwined with the way we process sensory information and memory. Memory, anticipation, and the passage of time. Our perception of time depends heavily on our ability to remember the past and anticipate the future. Without memory, we would have no sense of past events. Without anticipation, we would have no sense of the future. Memory, in particular, provides the structure through which we understand the passage of time. We remember what happened, we learn from past experiences, and we use that information to inform our future decisions. Our memories give us a sense of continuity, allowing us to perceive the present as part of an ongoing narrative of our lives. But the nature of memory itself is complex and not as reliable as we might think. Memories are not perfect recordings of past events. Instead, they are reconstructed, altered by our emotional states, our expectations, and the passage of time itself. The more we reflect on past events, the more our memories can become distorted. This phenomenon suggests that time, as we remember it, is not simply a direct reflection of reality, but is also shaped by the lens of our consciousness. Time is perceived through a filter of personal experience, and that filter, as we know, can be unreliable. Moreover, the ability to anticipate the future is equally central to our sense of time. Our future expectations shape our experience of the present. For instance, if we are looking forward to a future event, we tend to experience the present moment differently. Time seems to stretch or feel longer when we are anticipating something important. On the other hand, when we are involved in an activity, time can feel as though it passes more quickly. This experience is often referred to as time flies when you're having fun, a direct consequence of the brain's active engagement with the present. This relationship between memory, anticipation, and present experience creates the illusion of time's flow. Time feels like a continuous progression because our brains are constantly shaping the past and future into a coherent narrative. We mark the passage of time through our experiences, and those experiences create the story that we live out in our minds. But this narrative, like the experience of time itself, is subjective. Just as relativity tells us that time is relative to the observer, so too is the perception of time relative to our conscious experience. The brain's internal clock, how we measure time. How then does the brain measure time? The internal clock of the brain is a system that allows us to keep track of time even when there is no external reference, like a clock or a calendar. The brain has evolved mechanisms that allow us to estimate durations and perceive the passage of time even in the absence of obvious external cues. This internal clock operates in a way that is surprisingly flexible. It adjusts according to the context and our mental state. One well-known system that governs this internal clock is the circadian rhythm, which regulates our sleep-wake cycles and operates on a roughly 24-hour cycle. But this is just one of the ways our brain processes time. Our perception of short intervals, like the passing of seconds or minutes, relies on neurological circuits that can synchronize with external cues, such as a ticking clock. However, when we are immersed in an activity, our internal sense of time can become disoriented, and we lose track of the passage of time. Time seems to slow down or speed up, depending on the level of attention we give to it. The temporal lobe, a region of the brain involved in memory and sensory processing, is crucial for our understanding of time. Studies have shown that damage to the temporal lobe can lead to distortions in time perception, suggesting that our sense of time is deeply embedded in the brain's cognitive and sensory processing systems. Additionally, experiments have shown that when people are under stress, they tend to perceive time differently. Time may feel as though it has slowed down or sped up, depending on the emotional context. This variability highlights the plasticity of our experience of time, suggesting that the brain's internal clock is not an objective measure, but a malleable and subjective system that can shift with our mental and emotional states. The uncertainty of time. How does consciousness affect our perception of time? The relationship between consciousness and time is perhaps the most mysterious aspect of our experience. If time is a malleable, relative entity, as physics suggests, then how does consciousness experience it? How do we perceive time as flowing, moving forward, when the laws of physics suggest that time may be fundamentally different from the way we perceive it? Consciousness itself is an elusive phenomenon, difficult to define, challenging to study, and yet intimately tied to everything we experience, including time. The very fact that we experience time, that we can look at the world, recall the past, and anticipate the future, seems to suggest that time is fundamentally tied to our awareness. But if time, as we have learned, can stretch, bend, and warp, then how does consciousness fit into this picture? One of the most compelling theories about the relationship between consciousness and time is that consciousness exists in a kind of eternal present. While our minds store memories and anticipate the future, they do so by creating a narrative of time, a narrative that is constantly updated, with each new moment slipping into the past and new possibilities unfolding before us. This narrative may give us the illusion of time's flow, but it also suggests that consciousness is not bound by the same laws of time that govern the rest of the universe. Instead, consciousness may operate outside of the physical confines of time, experiencing the present moment as a continuous and uninterrupted flow. In this sense, time may not just be a measure of change. It may be the medium through which consciousness interacts with the universe. Time may be the lens through which we view the cosmos, giving our lives structure, meaning, and continuity. Whether time is an illusion or a fundamental aspect of reality, our experience of time, and the ways in which it shapes our consciousness, remains one of the greatest mysteries of the human experience. Time and the universe, the beginning and end of time. When we contemplate the nature of time, it is impossible to separate it from the history and future of the entire universe. Just as time shapes our individual lives, it also governs the vast cosmos, from the formation of galaxies to the eventual heat death of the universe. But time, as we experience it, is not merely a measure of the moments between events. It is intricately tied to the origin and the ultimate fate of the universe itself. The questions of where time began, where it is heading, and whether it has any real end are deeply philosophical and scientific, stretching our understanding of both cosmology and existence. The Big Bang, the beginning of time. The story of time begins with the Big Bang, the event that marked the beginning of not just the universe, but also time itself. According to current cosmological theory, the universe began as an infinitely dense point, a singularity about 13.8 billion years ago. Before the Big Bang, there was no space, no matter, and, crucially, no time. Time, as we understand it, emerged with the expansion of the universe. At the instant of the Big Bang, the universe began to expand from an incredibly hot and dense state. This expansion continues to this day, and it is the driving force behind the observable cosmic evolution. But the Big Bang does more than just mark the start of the universe. It also marks the beginning of time itself. Before the Big Bang, there was no before in the conventional sense. The concept of time becomes meaningless outside of the expansion that followed. This raises a profound question. What came before the Big Bang? Modern cosmology, based on the general theory of relativity and the cosmic inflationary model, suggests that time itself was born at the moment of the Big Bang, meaning that asking what happened before the Big Bang may not be a meaningful question. Time, as we understand it, simply did not exist before that moment. This is a deeply unsettling concept for those who imagine time as a fundamental backdrop to reality. If time is a creation of the universe itself, then is it possible that time has no true origin beyond the Big Bang? Some cosmological models, such as the cyclic model or the multiverse theory, offer potential answers to this mystery. In the cyclic model, the universe goes through infinite cycles of expansion and contraction, each one beginning with a Big Bang and ending with a big crunch. In this view, time is not a singular event, but part of a never-ending process. Each cycle is born anew, and time itself is a recurring phenomenon in the larger cosmic dance. Other theories, like the multiverse theory, suggest that our universe is just one of many, each potentially having its own timeline and its own beginning. The multiverse hypothesis suggests that our universe is part of a greater multiverse, where each universe within this multiverse could have had its own Big Bang and its own set of laws governing time and space. If this is the case, time is not just a feature of our universe, but a universal property that could exist in different forms across an infinite array of universes. Regardless of the precise model, the idea that time itself began with the Big Bang challenges our most basic understanding of reality. If time had a beginning, does that imply it has an end? Or is time an infinite feature of the universe, never truly beginning or ending, simply cycling through different phases of cosmic evolution? The heat-death of the universe. The end of time? As we continue our journey through time, we must turn our attention to its inevitable end. The future of time is inexorably tied to the fate of the universe itself. According to the second law of thermodynamics, entropy, the measure of disorder, tends to increase over time. This means that over the course of eons, the universe will gradually approach a state of maximum entropy, where no usable energy remains, and no processes can occur. This eventual state, known as the heat death of the universe, is one possible end to the story of time. In this scenario, the universe continues to expand, and the energy of stars and galaxies is spread out to the point where all matter becomes increasingly diffuse. Stars will burn out, galaxies will drift further apart, and the universe will become an ever colder, darker place. At this point, all meaningful events will cease to happen. Time will still pass, but there will be no change, no movement, no life. The universe will become a frozen expanse of empty space, a place of no energy, no activity, just a vast, unchanging void. In this state of maximum entropy, the passage of time itself becomes inconsequential. There will be no energy to fuel any process, and everything will become static. This scenario presents a rather bleak view of the universe's fate, but it is one that aligns with our current understanding of cosmic evolution. As stars run out of fuel, and as black holes slowly evaporate over trillions of years, the universe will enter a period where it is completely isolated from any further events or interactions. Time will not cease to exist, but it will lose all meaning. The universe will be a cold, dark, lifeless place, a universe of pure, uniform entropy. However, not everyone agrees that heat death is the ultimate fate of the universe. Some theories suggest that dark energy, the mysterious force responsible for the accelerated expansion of the universe, might play a role in determining the universe's ultimate fate. If dark energy continues to grow stronger, it could lead to a Big Rip, a cataclysmic event where the universe's expansion accelerates so rapidly that galaxies, stars, and even atoms are torn apart. In this scenario, time itself could be ripped apart, leading to a final end that might be more violent and chaotic than the heat death. The role of time in the universe's evolution. Even as we consider the possible end of time, we are reminded that time is not just a backdrop to the universe. It is a critical factor in its evolution. The age of the universe, its expansion, the formation of stars and galaxies. All of these processes are governed by the passage of time. Time itself is inextricably tied to the forces that shape the universe. Take, for instance, the formation of galaxies. The first galaxies began to form around 1 billion years after the Big Bang, as matter clumped together under the influence of gravity. This process of galaxy formation took place over billions of years, with stars being born, living, and dying in an ongoing cycle of creation and destruction. This cosmic evolution is a direct result of the flow of time. Without time, there would be no history, no unfolding of events, no changes in the structure of the universe. Time also plays a crucial role in the life cycle of stars. A star is born when massive clouds of gas collapse under gravity, and it burns fuel for millions or billions of years before it exhausts its energy. Some stars, like our Sun, will eventually expand into red giants before shedding their outer layers and becoming white dwarfs. Other stars, much more massive, will explode in a supernova, leaving behind black holes or neutron stars. This process of birth, life, and death is all governed by time. The same is true for planetary systems. The Earth, for instance, was formed over billions of years through the accretion of matter around the Sun. Our planet is still evolving, with tectonic processes, erosion, and the changing climate all shaped by time. Life on Earth, too, has evolved through time, with species arising, changing, and going extinct over geological eras. The universe is a dynamic, ever-changing place, and time is the thread that connects every aspect of its existence. From the Big Bang to the heat death or the Big Rip, time is the driving force that shapes everything. The end of time is not just the end of a human story, it is the end of everything. The universe's ultimate fate is inextricably linked to the flow of time, to the changes that occur in the cosmos, and to the gradual increase in entropy that dictates the ultimate destiny of the universe. What lies beyond the end of time? As we approach the end of this exploration into the nature of time, we must confront one final question. What lies beyond the end of time? If time does indeed end, whether through heat death, the Big Rip, or some other scenario, what happens to the universe? Is there a future beyond this final end? Or is time itself the ultimate boundary of existence? Some theories, like the cyclic model of the universe, propose that the end of one universe could be the beginning of another. In this model, the universe undergoes a cyclical process of creation, evolution, and destruction. Each cycle of the universe begins with a big bang and ends in a collapse, either a big crunch or heat death, only to start again. This model suggests that time is an eternal, never-ending cycle, with the universe repeating its birth and death in infinite loops. Other theories suggest that time itself could cease to exist entirely. In a universe at maximum entropy, where all matter and energy are spread evenly and there are no gradients of energy left, time might become meaningless. Without events, without changes, the concept of time might have no relevance. In this state, the universe would be static, frozen in time. And yet, for all the answers science provides, there are still mysteries about time that remain unsolved. What is the true nature of time? Is it a fundamental aspect of reality, or is it a construct of consciousness? What is the origin of time, and does it have an end? These questions, though deeply rooted in scientific inquiry, are also philosophical. They challenge us to consider the nature of existence itself and our place in the unfolding story of the cosmos. As we close our investigation into the nature of time, we are left with a profound truth. Time is not just something we experience, but something that shapes the very structure of reality. It is the thread that connects the past, present, and future, and its ultimate nature remains one of the greatest mysteries of both science and philosophy. Time, in all its complexity, remains an enigma, a force we can measure, experience, and observe, but one whose true essence may be forever beyond our grasp. Is time an illusion? The philosophy of time. As we approach the final chapter of this journey, we must grapple with one of the most profound questions of all. Is time an illusion? The more we delve into the mysteries of time, its flow, its relativity, its role in the universe, the more we are faced with the possibility that time, as we understand it, may not be as concrete or as real as we have always assumed. What if time is merely a construct of the human mind, an illusion created to make sense of the vast, incomprehensible universe? What if the passage of time, the very rhythm of our lives, is not a fundamental feature of reality, but a product of perception, shaped by the limits of our consciousness? To ask whether time is an illusion is to confront the very nature of reality itself. If time is a construct, then what is the nature of the universe we live in? What is the nature of existence, of events, of change, if time is not the constant, ever-flowing river we have always believed it to be? These questions touch on the heart of philosophy, science, and consciousness itself, and they force us to reconsider everything we thought we knew about the world. The idea that time may be an illusion is not a new one. Philosophers have debated the nature of time for centuries, questioning whether time is a fundamental aspect of reality or merely a human perception. The ancient Greek philosopher Heraclitus famously said, "You cannot step into the same river twice." This statement suggests that time is not a static force, but something that is constantly changing and moving, an ever-flowing current that cannot be pinned down. Heraclitus saw time as a force of perpetual change, something that was always in motion, never fixed. But was he right in seeing time as an illusion of change, or was he merely pointing to the deeper mystery of time's true nature? Immanuel Kant, one of the most influential philosophers of the 18th century, argued that time is not something that exists independently of the mind. According to Kant, time and space are not properties of the external world, but are forms of intuition, ways in which we perceive the world. In his work, Critique of Pure Reason, Kant suggested that time is a framework for organizing experience. It is the lens through which we view the world, not a feature of the world itself. For Kant, time is an illusion in the sense that it does not exist as an independent entity outside of our consciousness. It is a necessary construct of the mind, shaping how we experience reality, but it is not an inherent property of the universe. The question of whether time is an illusion also touches on the nature of reality. If time is a mental construct, then how do we account for the apparent passage of time in the physical universe? How do we explain the movement of stars, the birth and death of galaxies, the aging of living organisms? The evidence of time's passage seems undeniable. We feel the ticking of the clock. We see the stars move across the sky. We watch our own bodies age. These are not illusions. They are tangible, physical phenomena. And yet, as we have seen, modern physics tells us that time, at least on the fundamental level, is far more mysterious than we ever imagined. Time is relative. It can bend, warp, and stretch, and it can behave in ways that defy our everyday experience. One of the most intriguing implications of modern physics is the idea that time may not be as linear as we perceive it. In the theory of general relativity, time is intertwined with the fabric of space itself. Time is not a separate entity that exists independently of space. It is part of the same continuum, a dynamic feature that changes with the curvature of space-time. The more massive an object is, the more it bends space-time, and the more time is distorted. This means that time is not fixed. It is influenced by the presence of mass and gravity, and it flows at different rates depending on where you are in the universe. Time is not absolute. It is a relative experience that depends on your position and motion through space-time. Furthermore, in the world of quantum mechanics, time behaves even more strangely. In the quantum realm, particles do not move in a continuous, predictable fashion. They exist in a state of probability, fluctuating between different states and positions until they are observed. The passage of time in the quantum world is not as straightforward as in the macroscopic world. Events can appear to occur simultaneously, and particles can move backward in time or be entangled across vast distances, leading to paradoxes that challenge our understanding of cause and effect. If time behaves so unpredictably at the quantum level, what does that say about the nature of time in the larger universe? These revelations lead to a troubling realization. Time may not be the simple, objective force we thought it was. Instead, it may be a product of our consciousness, a framework that we impose on the world in order to make a sense of our experience. Time may be an illusion, shaped by the limits of human perception and the way we interpret the events of our lives. The flow of time may be a trick of the mind, a way of organizing the universe in a way that is understandable and meaningful to us. But if time is an illusion, what does that mean for our sense of self, for our memories, for the events that shape our lives? If time is an illusion, then change itself becomes a more profound mystery. How do we account for the constant changes in the universe, the birth and death of stars, the evolution of life on Earth, the growth and decay of galaxies? These changes seem to happen within time, yet if time itself is not real, then what drives change? What is the force that propels the universe from one state to another, if time is nothing more than a construct of the mind? These are questions that remain unanswered, questions that lie at the heart of both physics and philosophy. Despite the uncertainty surrounding time's true nature, there is one undeniable fact. We experience time. We feel its passage. We observe its effects, and we live through its flow. Whether time is real or an illusion, it is a force that shapes our lives and our understanding of the universe. The way we experience time, our memories, our anticipation of the future, our awareness of the present, is central to who we are. Time gives our lives structure. It gives us purpose, and it provides the framework in which we live our stories. But the more we explore the true nature of time, the more we realize that time, like the universe itself, is full of mysteries. It is a force that we cannot fully understand, a phenomenon that stretches beyond the limits of human perception and experience. Time may be an illusion, or it may be a fundamental aspect of reality, one of the most essential components of the universe, shaping everything from the birth of stars to the nature of consciousness itself. But in the end, perhaps it is not the nature of time that matters most. Rather, it is how we live within it, how we experience it, and how we move through its flow that defines our existence. As we conclude our exploration of time, we are left with a profound question. What is time, really? Is it an illusion, or is it the very fabric of reality? The answer may never be fully known. But what we do know is that time is a mystery, a force that governs the universe in ways we are only beginning to understand. Whether time is real or illusory, its effects are undeniable, and its significance is woven into every aspect of our lives. And, perhaps, in the end, that is the most important thing, that we are here, experiencing time, experiencing life, and trying to make sense of it all. Conclusion. What does the illusion of time mean for our understanding of reality? As we reach the end of our journey through the labyrinth of time, we are confronted by a profound realization. Time, as we know it, may not be as simple as we have always believed. It may not be the unchanging, constant force we once thought it to be. Instead, time is elastic, relative, and possibly even an illusion, a construct of the mind shaped by our perception, experience, and the limits of our consciousness. In the earlier chapters, we explored the fascinating theories of time as described by Einstein's relativity, quantum mechanics, and the second law of thermodynamics. We witnessed how time can be stretched, compressed, and warped by gravity, motion, and the very structure of space-time. We discovered that time is not a universal constant, but something deeply subjective, shaped by the observer's perspective, the forces around them, and even the speed at which they are traveling through the universe. We learned that time, at its most fundamental level, is intricately tied to the universe itself, woven into the very fabric of space, energy, and matter. Yet, despite these groundbreaking insights, we find ourselves faced with an unresolved question. What is the true nature of time? Is it a real, fundamental feature of reality, woven into the cosmos like the stars and galaxies? Or is it merely a perception, a trick of the mind, a tool we use to make sense of our place in an ever-changing, ever-expanding universe? Is time simply an illusion of the human consciousness, a construct of the brain's need to organize experience, or is it a true force that governs the course of cosmic events? As we ponder these questions, we come to a humbling conclusion. The mystery of time may never be fully solved. Time, in its most profound essence, is something that exists outside the boundaries of human understanding. It is a force that governs not just our lives, but the very existence of the universe itself, yet it remains elusive, difficult to define, and even harder to comprehend. Time is both a part of the fabric of reality and a construct that exists only in our minds. It is a paradox, a mystery that stretches across the cosmos and permeates every aspect of our experience. This uncertainty is perhaps the greatest revelation of all, that time, in its essence, is not a fixed or permanent entity, but something that is inherently subjective, shaped by our consciousness, our perception, and the universe itself. Time may not be the straightforward, linear progression we experience in our daily lives. Instead, it may be a fluid, malleable phenomenon that bends and shifts with the forces of gravity, motion, and our very perception of the world. Time is as much a product of the mind as it is a force of the universe, an intersection of subjective experience and objective reality. If time is indeed an illusion, then what does this mean for our understanding of reality itself? Does this revelation undermine the very structure of existence? Or does it instead provide us with a deeper, more profound understanding of the universe and our place within it? If time is malleable, uncertain, and relative, perhaps the universe itself is not as fixed as we once thought. Just as time can stretch and bend, so too can our understanding of the cosmos. Reality, it seems, is not a rigid, unchanging structure, but a dynamic, evolving entity, one that shifts and changes based on the forces that govern it and the perception of those who experience it. This realization, though unsettling, is also liberating. It suggests that we are not merely passive observers of a predetermined universe. We are active participants in a cosmic dance, experiencing time not as a fixed backdrop, but as a fluid, dynamic force that we are part of. Our experience of time is a reflection of our place within the universe, a narrative that we are constantly creating as we move through it. We are, in a sense, both the storytellers and the story itself, our consciousness shaping our perception of time and the universe, even as the universe shapes our consciousness. The implications of this understanding stretch beyond science and into the very heart of philosophy and consciousness. If time is relative, subjective, and ultimately an illusion, what does this say about free will, choice, and fate? If time is a product of the mind, can we truly alter its flow, or are we trapped within its current? What does it mean for our existence if the passage of time is not a constant, but something that depends on the forces of the universe and the nature of our consciousness? In the end, the illusion of time may not be an answer to the mystery of existence, but a doorway to deeper questions. It forces us to confront the nature of reality itself, how we perceive it, how we experience it, and how we relate to the universe around us. Time, as we have seen, is more than just a measurement or a tool. It is a profound force that shapes our existence and our understanding of the cosmos. Whether it is real or an illusion, whether it flows in one direction or stretches and bends across the fabric of space-time, time is an intrinsic part of the universe's story, a story that is still unfolding, one moment at a time. As we close the book on our exploration of time, we realize that the more we learn, the more we understand how little we truly know. Time, as we experience it, may remain a mystery, a question with no simple answer. But in the search for answers, we find something even more valuable: the willingness to explore, to ask questions, and to challenge our assumptions about the universe and our place within it. In the end, The mystery of time may never be fully solved, but it will always remain a central part of our quest to understand the nature of reality itself.